Hey, it's Tony from Adafruit, and in this video I'm going to look at MicroPython and this framebuffer module. So this will be a little bit of a technical deep dive into the framebuffer module, but it's relevant for CircuitPython and MicroPython because in CircuitPython specifically, to use some displays like the SSD1306 OLED, you need to use this framebuffer module, but you might not be able to fit that framebuffer module into memory. And so I'll show you some optimizations and a Python implementation of this framebuffer module that will let you use the SSD1306 and other displays in the future with your boards, even if you don't have a ton of memory. So I'll show you some interesting things, but we'll just kind of dive into and look at interesting things with how C modules are implemented in MicroPython and some of the trade-offs of C modules versus Python modules. Because actually in this video we're going to look at this framebuffer module, which has a C implementation, but I've created a Python implementation of it, and we'll look at the pros and cons and when you might want to use one versus the other, and why I kind of created it and what we want to do with it. So let's just kind of dive in here and we'll get started. And by the way, too, I have a new camera set up, so hopefully this is working well. We'll see when this goes up on YouTube. So just trying out a little bit wider angle here to see more of the room. But let's go back to the main view, or let's go to the main view rather, with desktop and everything here. So for this video, in the upper right hand corner, I have a Feather. This is the AT-SAMD, or the SAMD21 Feather. This is the Feather M0, the Adalogger version. So this is running CircuitPython, running the latest 0.8.4 release. Just came out yesterday, just bug fixes basically in that release. So it's got the latest code running on it. And then on top of the Feather, so the Feather, you can connect boards to it, I have the SSD1306 OLED display. And I've done a few different videos on using this display. I'll put a link in the description below when this goes up on YouTube, so you can check that out and see there's a whole guide on how to use this display with both MicroPython using its machine API and CircuitPython using kind of the newer API that we have that simplifies. Because on this SAMD21 processor, you have to use CircuitPython, which has a slightly different API. We can't fit in the machine API, but we've got a library for both of those, so you can use it with either one. Okay, so let's go in and I'll show you real quick. I'm going to try to use this display, and if you're running the latest 0.8.4 release and even the 0.8.3 release, you might run into a problem, and I'll show you how to fix it, how to work around it, and then we'll dive into more details about what this framebuffer module is, and just some of the interesting differences between C and Python implementations of modules. So hopefully you'll learn a little bit about some of the inner workings of MicroPython with this. So let's look at, first of all, this is the guide that explains how to use this display. And again, it talks about how to use this with both MicroPython and CircuitPython, and it shows you how to download. There are two different libraries, so you download the correct library. Now, like I said, with CircuitPython, we'll go through the steps real fast, and we'll try to get this working on the SAMD21 board. This will actually work just fine on the ESP8266, because I'll explain in a moment, it actually can fit in this module, whereas on the SAMD21 we don't have the memory to fit this framebuffer module. So there's a little bit of a trick that we have to make it work. So I've got my hardware set up already for this. I'm going to jump to the software page. This explains there are two different modules. There's a MicroPython version and a CircuitPython version. I've actually already got the library installed on my board. So if you look at this CircuitPython drive, which by the way, in the latest 0.8.4 version of CircuitPython rather, the drive is now called CircuitPy for the SAMD21 processor. So when you connect the processor, the chip to your board, to your computer, it shows up as a USB drive. You can drag your Python code onto it. Now it has the name CircuitPy. It used to be MicroPython. So just making it match the name of the release here, which makes sense. So you can see I've already copied over the bus device, register, and SSD1306 libraries. This guide explains exactly how to do that. It'll link you to more information, especially on Mac OS X. I've talked about this in a previous video. You need to do a special copy command to copy these files onto your board, because OS X adds all of this extra metadata that turns into these 4 kilobyte large files. It's not good, but it's easy. You just run these copy commands and it works fine. So I've copied these over, and then I'm going to open up the REPL, the serial, or the command terminal for my Python board. So I'll use the screen command, and it shows up as USB modem, 115200 baud, and I get connected, and here's the Python prompt. And then I'm just going to go through and start running some of this code to import the module. And I'm going to use the CircuitPython specific code. Look at the guide. It explains exactly the differences and when you need to use one versus the other here. So let's first import the board module. This gives you access to all the pins. And then let's import the native I/O module as I/O. So this gives you access to the I2C and all kinds of other interfaces. And again, I've talked about before in CircuitPython, we have a difference between native implementations, which use the hardware built into the microprocessor, versus bit-banged or software implementations for things like the I2C protocol. So on the ESP8266, you have to use a software or bit-banged I2C protocol because the ESP8266 doesn't have an implementation of the I2C protocol, but it's easy enough to kind of fake it at a slower speed. Whereas on the SAMD21, it has a little bit more peripherals, surprisingly, and it has a I2C interface that you can use. And so it's under this native I/O interface. And I've talked about this in a previous video about kind of CircuitPython and some of the differences between the machine API and the native I/O and the bitbang I/O API. Anyways, okay, so that's some of the boilerplate setup. And then I want to import the Adafruit SSD1306 module, and I guess I'll just import it under a slightly shorter name so it's easier to access it. Okay, something just failed. So if you try this right now, like I said, on the latest versions, you're going to get this error, no module named framebuff. What do we do now? So let's just kind of dive in real fast, and I'll explain what this framebuff module is and how we can fix this on the SAMD21 port. Now, you won't run into this problem on the ESP8266 port because it actually has this framebuff module. So first of all, let's just look at what is the framebuff module. So if I go to the main MicroPython source code, this is the upstream version. This isn't the CircuitPython version, the one that Adafruit has, but our version is exactly the same for this pretty much. And the interesting thing is, if you look at the source code for MicroPython, there's basically a directory for each port. So there's a directory for the ESP8266 port. There's a directory for the STM port. This is the Pi board, the STM32 microprocessor port. And inside of each port, there's a lot of different things that each port can define, but there's one file in particular that's very useful. It's this mpconfigport.h header. And I think pretty much all of the ports are structured in this way. They have this single header file. And there are all of these defines that you'll see inside of here that basically have like 0 and 1 values. So these turn on or turn off features of MicroPython. And there are a lot of features in MicroPython. And so you can see there's all kinds of things in here that this is the ESP8266 port, and it turns on a lot of things. And if I search for framebuff, notice right here, there's a MicroPy framebuff define right here. And this define is set to a value of 1 for the ESP8266 port. And so what this does is this tells MicroPython when it's compiled for this port, this header is included, and this header will turn on this little define. And when that define is turned on, then that adds into the source code or the firmware that's built this framebuffer module. So you might be wondering, okay, where does this framebuffer module live? And it's actually inside of the root MicroPython folder, so one level above this ESP8266, there's this xtmod directory, external modules. So these are modules that all of the ports can share because they have a generic implementation. You know, there's no ESP8266 specific code inside of this xtmod directory. All of that specific code should be inside of that ports folder. But there's still some very useful generic stuff in here. There's stuff like a random number generator, WebSocket stuff it looks like, SSL support using some external libraries and things. But here is where you can actually find this mod framebuff.c file. So this is the implementation of the framebuff module, and it's actually what's failing right here when, what this error means is that it can't find this framebuff module. So this source code right here is not compiled into the SAMD21 port right now. And I won't go too far into this source code. It's basically a C implementation of basic pixel commands. So this takes a chunk of memory, which is your display memory. So for this SSD1306, it's like a 1-bit display. So in a byte of data, it can pack like 8 pixels worth of display data. And it takes that buffer of data and a pixel format, and then it implements your basic, put pixel, get pixel, draw line, draw rectangle, fill a rectangle. It actually has text drawing and stuff built into here, although in previous videos I've shown I have a separate text library that can use like external fonts and things. But all of that is in a nice C implementation, so it's really fast. Like, this is native code, so you can look at this code and like, here's how, for example, Let's see. Let's look at this MVLSB set pixel function. This is actually how the pixel for this SSD1306 display is set in the frame buffer memory. And so it's just indexing into this byte array right here. It figures out where it needs to index into there based on the X and Y positions and like the stride of the display and all kinds of interesting things. And then it finds where it needs to set this pixel, and it just does some bit manipulation because it knows if the color is true or set to 1, then it needs to turn that pixel on. So it does some masking to say, okay, find the byte that has this pixel of data, and then just tweak that byte, or that bit rather, to be on or off. And so you can do that with some bit masking commands right here, like some Boolean operations. Kind of fascinating stuff to, if you're interested in this, to kind of step through this and reason about, okay, what does this Boolean OR operation do? And then they're doing this negation and some of these bit shifting to move the bits to the right position here. It's always kind of cool to just sit down and step through and kind of draw it out on paper and intuitively start to understand how these bit manipulation things work. But basically this cryptic line right here is just setting a bit within a byte on or off. But to do that, like there's no nice single instruction in Python that says, read this byte and change this bit inside of it. You basically have to read the whole byte and then mask out the bit that you want to flip and then set that bit the correct way. So it's kind of typical thing. But anyways, all of this is in C, so it's really fast because C is, there's no overhead of interpreting this code. You can write this code in Python. Python has bit manipulation commands, which we'll see in a moment here, but that has to be interpreted. The MicroPython interpreter has to turn that into bytecode, and then it has to execute that bytecode, and so there's all that overhead here. Whereas this just turns directly into assembly, like SAMD21 assembly language that will manipulate that bit in memory very quickly, like within a few clock cycles probably. So this is really fast. The downside is, unfortunately, this takes up space in the MicroPython firmware. So this is, let's see, this is about 500, almost 600 lines of C code. That's going to compile down into a few kilobytes, and this you actually don't even see. This includes this font file inside of here, and this font file is just a bunch of data which gets compiled into your MicroPython firmware. And so you might want that when you want speed, because it turns into assembly language code, which is a lot faster, but it takes more memory in the firmware. And on this SAMD21 processor, you don't have a ton of space for the firmware. I think we have, I think it's 64K total. I can't remember exactly how much flash memory we have, but there's a limited amount of flash memory, and some of that flash memory we have to use for the file system so that you can load your Python scripts onto the board. So that just takes away more space from what you can load into the MicroPython firmware. So unfortunately, you reach a point when you're developing the firmware where you want to add more features, but you don't have the memory in the firmware to do it anymore. And this frame buffer module is one case we kind of ran into where we realized we're out of space to add new things, even just syncing the latest additions to MicroPython. So we had to start looking at, okay, what can we do now? Can we pull this module out? Can we remove the frame buffer module? And you can just by flipping that little bit that I mentioned. So in that config files here. So again, like in the ESP8266, in this MP config port, you can turn this on and off, this MicroPython frame buffer. So we can set this to 0 and it won't compile in the frame buffer module anymore. And you actually end up saving, like, I think it's around 4 kilobytes of data in the firmware, which is pretty significant. So that's what we did. And actually, if we look at the CircuitPython source code, so this is our fork of MicroPython that adds the SAMD21 processor support. So if I look at the atmel SAMD directory here, and then in the boards directory, because we have different versions for each board, in the Feather M0 Basic, we should be able to see here in the MP config board, we don't actually see anything like your, like that, what's the name of it? It's MicroPy framebuff. It's not defined on inside of here. And so that's actually why when I try to import this SSD1306 module, I'm getting this no module named framebuff module error because it wasn't compiled into the firmware here for this. And so you can kind of see, now on some boards we do have this compiled in, like the M0 Flash. I think that we have this in right now. Well, maybe not. I'll have to look at this later. So and I might be wrong on the structure of this, but so for some of the boards, we will be able to fit some extra modules like this in, because for these external flash boards, they have an extra chip. There's a SPI flash chip where we can store the user file system with all of your Python code and all of your assets and other files. We put that into an external flash memory chip, and then all of the flash memory built into the microprocessor can be just for the MicroPython firmware. So all of that 64K or 128K or however much memory the SAMD21 has, all of that can be for MicroPython, and so that gives you a little more extra room to add back in these modules like framebuffer. Okay, so what do we do now? How do we fix this problem? I don't have a framebuffer module built into my MicroPython firmware. Can I add one somehow? And it turns out, yeah, you can, because again, just looking at this framebuffer code out in the xmod directory here, you know, it's C code, but it's just manipulating memory. It's not doing anything magic. You know, if I go back into here, it's really just operating on an array of bytes and just setting pixels to certain values. It's not running special assembly commands or things that require like low-level access to the hardware. It's just a C implementation, mostly for speed and convenience here. So what I did is I actually took that C code and converted it into Python code. So I made a new module. I call it MicroPython-Adafruit-framebuff. And I call it this because it's not CircuitPython specific. This can work with MicroPython, and that's my intention here, that you can use this as a drop-in replacement for the C version of the framebuff module. But you can use this where for some reason you can't use that C version. Like maybe your MicroPython firmware doesn't have enough room to add that module to it. So, you know, you can add this as Python code because maybe you have room in your file system, you know, whether you use an external flash chip or maybe you've just made that trade-off where you've given less space to MicroPython and more space to your user's file system here. So that's what I've done, is I've converted this code from C into Python code. And it's very similar. I won't go into all of the details of the code, and it's actually not all totally implemented yet. There's enough implemented to use the SSD1306, and other TFT displays should work, but I haven't tested them yet. But you know, again, I figured I'd kind of show kind of the progress on this. But I've basically taken all of these operations. So like we saw that MVLSB set pixel function, you know, the C implementation of it is right here, and then the Python implementation of it is right here. And it's really similar. Because luckily, you know, in Python, it has exactly the same bit manipulation operations as in C. So, you know, you can shift your bits in a byte different directions, you know, using this greater than or less than command. You know, you can do a Boolean AND, which basically tests, you can see or you can mask out certain bits in a byte exactly the same way that you would do it in the C code, like right here. Now, the one difference is in C, you have fixed size types. So this size t, this is usually I think like an 8-bit value, depends on each platform, or there's like a uint 8t, this is an unsigned 8-bit value for this offset variable, whereas in the Python code, I don't have that. I just have a variable called offset that's going to be set to that value. Now in most cases this doesn't really matter because a number is a number, and if you're just doing simple operations like addition, subtraction, division, you don't really care. But sometimes you do care because when you get to the limits, you know, in the C code, this is an 8-bit value. So if you have a value that's like 254 and you add 2 to that, it's going to overflow. It's going to go beyond 255, which is the limit of an unsigned 8-bit value, and it'll roll back down to the value 0. Whereas if you do that in Python, if you have a value of 254 and you add, in fact, I'll do it right here in the REPL, you know, 254 plus 2, you get a value 256. You don't get that rollover behavior or that overflow behavior, and there's underflow is a similar thing. So that's a very subtle thing, and you kind of have to look at your code to understand, do I depend on that overflow behavior? And you can get the semantics of overflow. So in Python, if I wanted to do this, I could say 254 plus 2 and OXFF, because this will mask out and say, okay, ignore all the upper level bits. I only care about these low 8 bits. Basically, I'm looking at the low byte of this. And so now you see I get a value of 0, because even though it did 254 plus 2 and got a value 256, only looking at that low byte, you see that overflowed value to 0 there. And so that's how you can kind of emulate fixed size types in Python by doing some of this masking. Now, luckily, I kind of looked at this code and realized, like, okay, I don't really depend on the overflow semantics for this bit manipulation here, so I don't have to do that. But something to be aware of, that you can't just take your C code and directly run it in Python. Even if the syntax is the same, it might work if you're lucky, but in a lot of cases, you're probably going to run into these very weird edge cases. And it's tricky because, you know, overflow and things like that are usually these edge cases that you don't think about until it's too late. So again, be careful when you're converting code like this. But in the Python code, you know, it's really not too crazy. I'm doing all the same bit manipulation things like anding. This is kind of a negation where you take all the value. So if I take the value 0x00, 0, but if I negate that 0x00, then, well, that's interesting actually. If I do that and then and it with 0xff, now I get a value 255. So again, you're seeing some of the what's happening here is in Python, numeric types are signed. They can be negative or positive. Whereas in C, you can choose. Like, you pick whether you want this variable to be unsigned or signed. And if it's unsigned, that means it can't have negative values. And the way you represent negative numbers in a computer, usually you set this high-level bit. It's this thing called 2's complement math. If you study computer science, you will learn a lot about this. But basically, if you set this high-order bit, it tells you, oh, this is a negative number. And in Python, all numbers can be negative potentially. So when I inverted the value 0, it flips all the bits on, but then Python kind of interprets that as a negative value. But if I mask out that lower byte by doing this Boolean and, then I kind of say, okay, ignore all that signed stuff and just look at these 8 bits and give me the value. And because 0 inverted turns into all 1, you get a value of 255, which is every bit flipped on, basically. So again, I guess this is another good example of be very careful taking C code and trying to convert it and use it directly in Python. You're gonna run into weird little quirks like this around signed and unsigned. But you can do it. If you're careful about it, you can make everything work in the same way as the C code. But again, it's going to be slower because this turns into Python bytecode, which is then executed by MicroPython. So this won't be as fast, but it's going to be functionally the same. And so I've implemented that framebuffer module, most of it. And so it has commands in here for setting pixels, horizontal lines, vertical lines. I haven't implemented yet line drawing, blidding, scrolling, and text. Because actually I have a separate library for that, which I might eventually merge back into this. So look at some of the previous guides I've done, and you can see I have a whole other library that implements all of those functions already. But again, my intention here is that I want to have a Python implementation of the framebuffer module so that you can choose if you're using firmware that doesn't have framebuffer implemented, but you really need to use the display. It's possible now. You can use this Python implementation as long as you have space in your board's file system to import it and use it. So, okay, enough talking about it. Let's copy over that framebuffer module. So, like I said, this is a MicroPython module. Go to the Releases tab, and there's a framebuff.mpy module. Download this file, and then copy it onto your board, the root of your board's file system. So for me, I have it in this directory here, so I'm going to copy it. And actually, I think I can just drag it. Well, no, I'm going to show you the proper way to copy it for the SAMD21 on Mac OS X. On Windows, you can just drag and drop and it's fine. On Mac OS X, because I downloaded this file from the internet, it flags it as a file downloaded. It adds this extra metadata, which turns into 4 kilobytes of data on the board. You'll fill up your file system, unfortunately, very quickly. It's a very annoying quirk. But here's what I want to do. I basically, so I can see my file is inside of here, this framebuff.mpy. I want to use CP with the -X, uppercase X option. That tells Mac OS X to copy this file, but ignore all this extra metadata like the bit that says it was downloaded from the internet. So copy that framebuff.mpy onto my CircuitPy drive. So I'm just going to do that, and it copied the file over there. Now if I look in the Explorer here, I can see, yeah, there's framebuff.mpy. Okay, so let's go back to our REPL here, and I'm going to press Control D, D as in dog. This just resets the board, and then I'll press Enter to turn off the auto reset logic. And okay, let's do this code again. So let's import our board module. Let's import native IO as IO. let's import Adafruit SSD1306 as SSD1306. And hey, we didn't get that error anymore. So, previously we saw error framebuff module not defined. Now it worked because I added this framebuff.mpy, which is an implementation that has pretty much exactly the same interface. So it should be compatible and should work. It's just going to be a little bit slower. Okay, so let's make the I2C interface. So we'll do this as board.scl and board.sda. This is exactly from the MicroPython guide on using this display. So I'm just using the CircuitPython I2C implementation. So we're down to this line right here, basically. So I do that. That creates the I2C interface. And now I can create my display. So if I create the SSD1306 module, inside of it is an SSD1306 underscore I2C implementation. This takes a few parameters. You need to give it the width in pixels, the height in pixels. So for the feather, it's 128 by 32, and then the I2C interface for it. So I do that, and okay, that worked. And, you might have seen it flash a little bit because it kind of just turns on the display, and you get some random display memory. And now I can do all the same operations. So display.fill1, this will set every pixel on. I do that. Now, nothing happened. That's because for these displays, you have to call display.show. And now I do that, and hey, look, it turned on. And then I can set all the pixels back to 0, and then I can do display.show, and it turns it off. Now, the big difference here, you might notice when I'm calling display.fill, like fill1, it's a little slow. Like, that took about a second to run, and it's it's only setting like that 128 by 32 pixels. When I call show, they're all turned on now, and that's where you start to see the trade-off. Is that it's no longer the C code that's running. It's not running this fast set pixel, and it's actually this fill rectangle command that it's using when it's doing that fill command. And so this is a very compact C implementation. It's not allocating memory. All of the variables are defined ahead of time. Everything's probably on the stack. It's very fast. It just does a while loop. It just blasts through all the pixels. It can use pointers to memory and index directly into them. It doesn't have to do all of this Pythonic stuff like looking up in a byte array things. So it's very fast and compact. This probably compiles down into a handful of assembly language instructions that are really fast. Whereas in the Python version of this code, we can look at the fillRect function, and it's a Python loop, but I'm setting variables, which this is going to do some allocations. The garbage collector might kick in after a certain point in time. This is going to do some allocations potentially with this range function, although I think they've optimized that. I'm doing lookups into a byte array, which has to call some functions, and there's some overhead there. And again, all of this is interpreted. So that's why you see it takes a little bit more time for this to run. But it runs, it works. Like I can turn on and off. Let's see, let's clear the display again. And then I'll set some pixels just to show that you can set them. So you set the X and the Y position, and then the color, either 0 or 1, on or off. So let's do the origin pixel. Let's do a pixel kind of halfway into the display, like 64 by 16. And then let's do the very last pixel, which would be 127 by 31. So if I do all that and then display.show, now you can see there are 3 pixels that are set. Basically your origin, the middle pixel, and then kind of that last position pixel there. So this works fine. You can even do, like, how about a horizontal line from 0, 0, and let's go across all 128 positions with the color 1. Oops, do I not have? Oh, that's right. The SSD1306 module doesn't have the horizontal line function implemented. It's only in the framebuffer module that's lower level. I think I can technically do. Oh, I forget what I called this. Let's see. Let's look at what's on the display object. It is. I think it's called buffer. So I think I can actually get to the lower level frame buffer with this buffer instance. So now if I do 0, 0. 128 across, value of 1. Oh, okay, never mind. I'm trying to show something a little more advanced. If you want to do graphics drawing, I've done a whole video. I have a separate library you can include. You give it your pixel drawing function, which is implemented by this framebuffer module, even the Python implementation, and then it gives you horizontal line drawing. It gives you, normal line drawing, circle drawing, triangle drawing, all that stuff is implemented in there. But again, it's not going to be fast because your low-level pixel drawing is using Python code to set that display memory, and so it's going to be a little bit slower. But the nice trade-off is your MicroPython firmware is smaller because it doesn't have that C implementation inside of it. So that's really all I wanted to show in this video. Is just there's this new MicroPython Adafruit framebuff module, and I'm going to update the SSD1306 guide to mention it because for some boards that run CircuitPython, like the SAMD21 Feather M0 Basic, any of the boards that don't have an external flash memory, you might not have the frame buffer module compiled in. And so if you get an error that says error importing framebuff, check out what I just showed in this video, check out this module, add this module, and things should work. You should be able to do all the same graphic drawing, your code should be exactly the same. It's just going to be a little bit slower because it's this trade-off here for speed. Speed versus memory, this is like the ultimate trade-off. If you ever do anything in computer science, you're going to run into that kind of a trade-off here. But it's good to have options. And again, this will work with any MicroPython board, so even the microbit, this would probably work with. I don't know if the microbit has the frame buffer module included in it. If it doesn't, then this should work. This would be an option there too, so you could use little displays with it on even that tiny little board. So anyways, I don't see any questions here, so I think I'll wrap up this video. We'll go back to kind of the main headshot here. So, and it gets a little stuttery for some reason. I'm still messing with the CPU utilization, but switched over. I'm using a GoPro camera, so I'm not sure I'll stick with this forever. But it's nice, nice wider field of view. And this is not actually as wide as it can go, but it's kind of handy to have some more options for streaming in cameras. So okay, I'll wrap this up. So thanks a lot for watching. Check out youtube.com/Adafruit. That's Adafruit's YouTube channel. You'll see this video, all kinds of other fun project videos there. Check out twitch.tv/Adafruit. That's where I like to stream these things live. And so usually every Friday, I just lost one of the lights. The battery just went out on it. Anyways, I like to stream every Friday, although this is a Thursday. That's just because tomorrow I'll be busy and so I won't be able to do a stream. So if you're going to do one today on this interesting subject with the frame buffer module. So if this is useful info, click the like, the comment, the subscribe, let us know this is good stuff, and we'll keep doing it. And look forward to a lot more CircuitPython and MicroPython videos in the future. So we've kind of hinted at, we've got all kinds of fun boards, like this is the Circuit Playground version that has the SAMD21 chip on it. So we'll see a lot more with CircuitPython in the future with that. So until next time, Tony from Adafruit. So thanks a lot for watching. I'll see you later. Bye.